Testing, 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 testing. 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 Why is this not starting? Testing, testing, testing. 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 All right, works. We're live. Okay. Welcome to another Hoopo stream. Today we're going to be looking at PyTorch 2.0. This is a new release of PyTorch, which is a deep learning framework. PyTorch actually recently met a announcement or something like that. So PyTorch is no longer being maintained by Facebook or Meta. It's now part of a PyTorch Foundation, which means that it's a separate organization. It is the most popular deep learning framework by a lot. So if you actually go into trends here, I love to show this chart, but PyTorch, you can see here, it has severely beat out TensorFlow. TensorFlow in the 2018s was about 50-50 with PyTorch, and then we got other things here, but we can see that PyTorch has largely exploded and become the de facto deep learning framework. And it is now part of its own foundation, so it will hopefully be separate from Meta and their kind of goals, and won't necessarily be driven by their product requirements, which is good because it's used pretty much by everyone. You want it to become the go-to open source framework and not an internal framework. So we're going to be looking at this getting started with PyTorch 2.0. They have kind of some analysis, some motivations, some charts that show you kind of what the new features are, what they expect, and so on. Let's get to it here. Introducing PyTorch 2.0. Let's make this a little bit bigger. Over the last few years, we have innovated and iterated from PyTorch 1 to the most recent 1.13 and moved to the newly formed PyTorch Foundation, which is part of the Linux Foundation. I did not know that. So they basically, I guess Linux is probably the best example of open source software that works and that gets maintained properly. So Linux is the operating system. I'm on a Linux system right now. This is a Ubuntu system, which is a variant of Linux. But it's interesting to see that PyTorch is now part of that. PyTorch's biggest strength is what we continue as a first-class Python integration, imperative style, simplicity of the API, and options. PyTorch offers the same eager mode development. So this is the kind of script-like behavior that you see in Python frameworks, where every code gets evaluated as soon as the kind of interpreter goes and reads that line of code, which is different from languages such as C++ or Rust or Go. Languages like that are compiled into some kind of executable, right? You could basically code that runs closer to the machine, and then you run that compiled code, versus PyTorch and Python, they basically run line by line. Okay, we are able to provide fast performance and support for dynamic shapes and distributed. So dynamic shapes, what they mean here is that when you have a computational graph within a deep learning system or a machine learning system, it's going to be very sensitive to the shapes of the tensors, right? If you kind of constantly change the shapes of the tensors, then it's very difficult to compile into a set of kernels and optimized code that run cleanly. So dynamic shapes is something that people want. And then, of course, distributed is something that people want, right? The ability to be able to run your code across multiple hardware devices. Below, you'll find all the information you need to better understand what PyTorch 2, where it's going, how to get started. A lot of learned developers look forward to the community. Okay. Faster, more Pythonic, and dynamic as ever. Today we announced torch.compile, a feature that pushes PyTorch performance to new heights and starts the move from C++ back into Python. Okay, so they're kind of leaning more into Python, it seems. Hence we call it 2.0. Substantial new direction. Hopefully it doesn't break existing code and it's backwards compatible. This makes me a little bit scared that it's not. Okay, never mind. They're saying it's 100% backwards compatible. Good. Underpinning torch compile are new technologies: torch dynamo, autograd, primtorch, and torch inductor. Torch dynamo captures Python PyTorch programs safely. Python frame evaluation hooks. Okay, safe graph capture. AOT autograd overloads PyTorch's autograd engine as a tracing autodiff for generating ahead of time backwards traces. So autograd is auto gradient, right? Basically the same auto diff. These are all, when you're doing a deep learning system, at the end of the day, you want to learn, right? And in order to learn, you need to push gradients. You need to update the parameters. In order to do that, you're going to need to find the derivative of some parameters with respect to an output or with respect to some other parameter. And all those derivatives, obviously they're expensive computationally to calculate. So you want to basically have systems in place that can automatically calculate those derivatives in a convenient way. And that's what autograds and autodiff are doing here. PrimTorch canonicalizes 2,000 plus PyTorch operators down to a closed set of around 250 primitive operators. Okay, that developers can target to build a complete PyTorch backend. Substantially lowers the barrier of writing a PyTorch feature. So, operators are actually operations that you would use as part of a deep learning system, right? As part of a model architecture. And over the years, the amount of operators available in these deep learning frameworks has kind of ballooned. So you can see here over 2,000 PyTorch operators. But for every PyTorch operators, somebody needs to write code that compiles it down into a CUDA kind of kernel or some kind of hardware code. So the more of these operators that you have, the more annoying it is to maintain that kind of like compilation code, right? So reducing it down to 250 primitive operators will reduce the maintenance overhead and hopefully make things a little easier. Hi, hi, yo, yo. Hey, hey, low, low. Torch Inductor is a deep learning compiler that generates fast code for multiple accelerators and backends. For NVIDIA GPUs, it uses OpenAI Triton as a key building block. So this is something that we read about in an article on this channel before, where basically people want to move away from NVIDIA hardware and be able to run their machine learning models on a larger variety of hardware from a larger variety of vendors. So you've seen kind of these, you've seen people such as OpenAI release tools like Triton that are basically generating fast code for multiple accelerator, right? You want to be able to compile all of these ops into the fast code that runs on a GPU, right? So in order to convert these 250 primitive ops or these 2,000 ops into fast code that runs on GPUs, you need a deep learning compiler, right? That compiles it to that. So that's what OpenAI Triton and Torch Inductor are doing. Okay, Torch Dynamo, AutoGrad, PrimTorch, written in Python and support dynamic shapes. The ability to send in tensors of different sizes without inducing a recompilation, making them flexible, easily hackable, lowering the barrier of entry. Use a diverse set of 163 open source models across various machine learning domains. Okay, so things like image classification, object detection, image generation, language modeling, Q&A, sequence classification, recommender systems, reinforcement learning. We separate the benchmarks into 3 categories. 46 models from Hugging Face Transformers, which is a library that we've used on this channel a lot, and then 61 models on TIMM. This is not TIMM. This is okay. So TIMM is just image models, but also using Hugging Face. And then Torch Bench, which I assume is maybe reinforcement learning, but bench just means benchmark, and then torch obviously comes from PyTorch. What is this? Open source benchmarks. Okay. Add a little star. How about that? We don't modify the open source models except to add a torch.compile call. Measure speedups and validate accuracy across these models. Since speedups can be dependent, we measure speedups on both float 32 and automatic mixed precision. Yeah, data type is important. So if you guys have been following kind of the AI world, obviously people have talked about, for example, compiling the llama and the alpaca models down to 4-bit precision, which means a data type that takes small amounts of compute and memory. And you can get speedups by using these lower data types. So float 32 compared to a float 16, float 32 would have twice as much memory. So automatic mixed precision is kind of the intelligent ability to change the data types such that your model can run faster. We report an uneven weighted average speedup of 0.75 plus 0.5. Okay. Torch.compile works 93% of the time. What does that mean? It doesn't work 7% of the time? Is that another way of saying it? The model runs 43% faster on an NVIDIA A100. Using a float 32, it runs 21% faster, and at AMP precision, it runs 51% faster. Yeah, so a huge amount of your performance gain is just going to come from using these lower precision data types. So that's going to definitely be part of the story here. Desktop class GPUs, such as an NVIDIA 3090, which is, I think, what we have on this machine. We've measured that speedups. Is it what we have? NVIDIA. No, this machine is two 1080s. Never mind. Default backend supports CPUs and NVIDIA's. Does not yet support other GPUs. Yeah. So it's interesting how, like, here earlier, right, they talk about deep learning compiler that generates fast code for multiple accelerators and backends. And it's like, oh, okay, so it's going to support a bunch of GPUs. And then you go here and they say, nope, we do not support anything that isn't an NVIDIA GPU, basically. Okay, speedups for torch.compile against eager mode on an NVIDIA A100. So this is on an NVIDIA A100, and then they basically, I guess, 76% speed up on Torch Bench, 52% speed up on the Hugging Face transformers, and then 38% speed up on the image models. You can try out the Torch compile in the nightly binaries, 100%. That's what we're going to try to do. Roadmap we developed to push the mode further. Some of this work is in flight. And then they have an Ask an Engineers 2.0 live QA. Okay, interesting. Some testimonials, motivation, technology. Can we just, is there a pip install here? So let's go on PyPy and we'll search PyTorch. So PyPy is basically all the PyTorch packages that are installable via pip. And here you can find packages that are called, for example, PyTorch, but these don't actually seem like the official one. Let's actually do the official PyTorch pip install. We'll go here, start locally. So we want PyTorch 2.0. We want the Linux version of that. Let's use Conda, because that's the environment that we have now. Let's use Python, and then which CUDA do we have? We have CUDA 11.6. Oh no, don't have it. Wonder if they have a CUDA 11.6 PyTorch. Let's see. So let's do Conda history grep Conda. Let's do this. So we're going to create an environment here. We're going to call it PyTorch 2. What Python version do we want? And whatever. Let's try Python 3.10, see if that works fine. And let's come back here. Let's copy paste this Conda installation instruction here. Let's see if we can get CUDA 11.6. You might not find this. Or it might just install an older version of it. Python 3.7 or greater. It's fine. We have Python 3.10. Solving environment, done. CUDA 11.6. CUDA 11.6. PyTorch 2.0, 3.9. PyTorch CUDA 11.6. I don't trust that. Let's go back to. Actually, let's try it. Let's try it. Let's install it with the 11.6, and then we'll see if it actually installs 11.6 or whether just it installs an older version of PyTorch. While that's going, let's continue to read some of these testimonials here. Sylvain Guger, primary maintainer of Hugging Face. With just one line of code, PyTorch 2.0 gives a speed up between 1.5 and 2x in training transformer models. This is the most exciting thing since mixed precision training was introduced. Okay. We still don't really know where that speed up is coming from. Is it coming from the better ops? Is it coming from just the better compiler? Is it just coming from this mixed precision? Right? This automatic mixed precision? So yes. Unsure. Luca Antiga, the CTO of Lightning AI and one of the primary maintainers of PyTorch Lightning. PyTorch Lightning is a it's like a framework on top of a framework, which, honestly, I wouldn't necessarily recommend. It's basically like they built a deep learning framework on top of PyTorch that has a little bit better syntax, a little bit more. It's a little bit more opinionated, so it makes decisions for you. So you don't have to like necessarily know a lot of what you're talking about, or a lot of what you're doing. You just kind of um, verbally condenses, syntactically condenses PyTorch. But I think the problem with these type of tools like PyTorch Lightning is that because they're built on top of a platform that changes, right? They themselves have to constantly change. So PyTorch doesn't necessarily talk to these people. So whenever PyTorch changes certain functionality in their code, maybe they change the names of certain functions, they change the way that certain abstractions work, then PyTorch Lightning has to like figure out what they did and then go back and modify all their code accordingly, and it can become a big maintenance kind of headache. But I don't know, 22,000 stars is pretty impressive, so maybe these guys are killing it. I'm just unaware. Okay. Embodies the future, the possibility to capture a PyTorch program with effectively no user intervention and get massive on-device speedups and program manipulation out of the box unlocks a whole new dimension. I mean, this sounds like a paid review. It just works out of the box. Okay. So let's activate our Conda environment. Let's see, Python, import PyTorch, or sorry, import torch. What? Wait up. Maybe it's Python 3, and then import torch. Pip freeze. Freeze into what the fuck is going on here? Certify file? Not what I want. Yeah, I mean, if we can't even import PyTorch, I don't think it even installed this. You may have to research. No, that's just Conda installation, apt install. See if we pip install torch. Torch 2.0, Many Linux 1, CUDA 11, CUDA runtime, CUDA 11, Floss, NVIDIA CUDA 11. There's Triton, so OpenAI's Triton. Data markup, built lit. Looks like we got something installed here. Okay. Python import torch. All right, we got torch. Torch.version. We have, this is it. PyTorch 2.0 with CUDA 11.7. So it might not, because GPU is available, right? Or torch.cuda is available. This might be no. True. Okay, good stuff. So this is good. I thought maybe that because we have CUDA version 11.6 on this computer, maybe the CUDA 11.7 wouldn't work, but it does seem like it works. So we do have PyTorch 2.0 with CUDA 11.7 on this computer now. It's perfect. All right, let's go back to here. Innovation. Philosophy on PyTorch has always been to keep flexibility and hackability on our top priority and performance as a close second. We strive for high performance eager execution, Pythonic internals, good abstractions for distributed autodiff, data loading, and accelerators. Okay, hardware accelerators have become 15 faster in compute and about 2 times faster in the speed of memory access. Yeah, it's really not the matrix multiplies that are the bottleneck anymore. It's actually the memory access and I/O that is the bottleneck. Moving internals into C makes them less hackable. Yeah. Performance limits of eager execution. Start a first research project. Preserve certain flexibility. Support for dynamic shapes. Dynamic programs, which researchers use in various stages of exploration. Here's we build several compiler projects within PyTorch. Let us break down the compiler into 3 parts. Graph acquisition, graph lowering, and then graph compilation. Torch.jit.trace. So JIT means just in time, which is basically another way of saying this kind of eager execution that they keep talking about, right? Where you execute it, you execute a program kind of line by line. Torch script, lazy tensors. Some were flexible, some were fast but not flexible, and some were neither fast nor flexible. Bad user experience, like being silently wrong. Okay, so what is this that they have here? They have a function called foo that has a 2D convolution here. Oh, and why don't we go into our dev folder? Let's go into Betterer. CD into PyTorch here. And let's touch examples, or let's do test 2. And then let's open that up. So we're going to do a little throwaway Python script here for testing these. We're going to say testing out PyTorch 2.0 functionality. I'm going to copy paste this here. Put that there. Of course, we're going to import torch. Say print torch version. That's what we want. And then we also is CUDA available. Want as well. Why don't we write this function here? So they have a foo convolution, which takes some input x. Then it does conv2d. So here we're going to need the import, the functional API. So the functional API provides a operations such as the 2D convolution in a functional way, which means that you give it your input. Let me make this a little bit bigger. This is probably really hard to read. But you give it your input, you give it your weight matrix, you give it your bias matrices, and then you get your y. The problem here is that weight and biases are not defined. You have to make them zeros. Also, the way that most of these are written is usually like this. We don't actually want a ReLU, we want the batch norm, specifically the 2D version of the batch norm. And we want the ReLU. So why isn't it finding this? Batch norm 2D does not exist anymore. Applies batch normalization. I guess maybe batch norm without the 2D is the same. See also torch 1D, torch 2D, torch 3D. So maybe batch norm 2D is now there's just a quark that you put into this and then you tell it that it's the 2D one. So one thing we can do here is wait and bias. Just initialize them to random global variables. Really, you wouldn't be doing this. This doesn't make any sense, but do that. And then return X. Okay. So fooconv. Let's make a random input. Input, or not random. Foo input. 1, 3 channels, 32 by 32. So this is a 32 by 32 image with 3 channels, and it's a batch size of 1. So fooconv output, and then print output. Yeah. So one thing, this is what GitHub Copilot is kind of like figuring out exactly what we're doing. So what we can do here is we can import time. And then here we can say start time. Time.time. And then you have that. Time taken to compile the graph. Start time. Output. Okay. So let's go ahead and run this, and you guys can actually see what's going on here. But we will run this. This is test2.py. CUDA is available true, batch norm 2, missing 2, running mean, and running variance. So we need to keep track of these. Batch norm mean, and then batch norm variance. Okay. Okay, let's not print the output because it's just a bunch of nonsense anyways. Okay, let's clear that and let's run it. So you see here how we called the same function twice, but the first time it took longer than the second time. So what is going on here? So what is happening here is that this is what eager execution and kind of just-in-time compilation is all about, right? And it's, if you've ever played with JAX, JAX does this very well as well, where basically the first time you call this, PyTorch is going to pay attention and it's going to say, okay, you have a convolution, and then you have a batch norm, and then you have a ReLU, and you're inputting a tensor of some specific shape, and then you're inputting a tensor of some other, and you're outputting other tensors of another specific shape. So I know what the shapes are, I know what these operations are, I know what the output is, so I'm going to basically compile this, and anytime you call this function in the future, I can basically just use the little compiled version of it that I have, which is what PyTorch is doing. So I can actually do compiled time, and then here we'll do original time. Then we can say speed up. There you go. 14x speed up, significantly faster. All right, and here you can actually see this is where, for example, the whole dynamic shapes becomes important, right? So one of the things that they keep talking about here is the fact that you want to be able to support dynamic shapes. Where is it? Where is it? On this dynamic shapes. Dynamic shapes. So what dynamic shapes is referring to is that the size of this input might be different. So one thing we could do here, for example, is this. Let's change this to 28 by 28. See, you don't get as fast of a speed up. Let's see if we change it. That's not what we want. Let's add this there. We'll do once like this, then we'll do once again, but after compilation, then we're going to change the input shape, and then we're going to run it again, see what happens. So we're going to do this here. Then we're going to do dynamic shape time, and we're going to print the original time versus the dynamic shape time. Let's see what we get here. Okay. Speed up 11 for the first one here, and then somehow 17 for this one here. So I don't know, maybe it's just a fluke. Maybe we should run this a couple more times just in case. Seems weird that the dynamic shape would be even faster than the non-dynamic shape one. Or maybe it's just because the dimensionality of this tensor is smaller. Let's try with a larger tensor here. So if we change the shape of the tensor but make it bigger, yeah, okay, this is more what I was expecting, right? So right, this is probably hard to read, but you're getting a big speed up by the fact that this is now compiled, right? The first time you run it, not compiled. The second time you run it, PyTorch has built a little basically optimized version of your function, and it uses that optimized version of your function. And we can change the shape of the inputs to that function, and the little optimized version of that function that PyTorch has created still works pretty fast. So that's what we wanted to see here is 10x speedups, 11x speedup here. So let's keep going. Torch Dynamo, acquiring graphs reliably and fast. We started working on Torch Dynamo, an approach that uses CPython called Frame Evaluation API. What's this? This is the Python Enhancement Protocol 523. This was created in 2016, so it's quite old now, it seems. Allow for the specification of a per interpreter function pointer to handle the evaluation of frames. Per interpreter function pointer. Okay, but basically they added that. They somehow used that in order to get you this Torch Dynamo. I don't know about using a bunch of old crusty GitHub projects to like determine whether PyTorch is backwards compatible, because do you really care about being backwards compatible with a bunch of GitHub projects that like nobody cares about anymore? I don't know. I suppose keeping the community alive is important enough for PyTorch that backwards compatibility is a huge requirement. This is what we knew. We had finally broke through the barrier, and we were struggling for many years in terms of flexibility. Okay. Fast code gen using define by run IR. Inspiration from how our users were running high performance custom kernels. We also wanted a compiler backend that uses similar abstractions to PyTorch Eager and was general purpose enough to support the wide breadth of features. Automatically maps PyTorch models into generated Triton code on GPUs and C++ OpenMP on CPUs. So I think one thing we can do here is, let's see if this changes anything. We're going to put everything on the GPU. It's like 2 device or something like that. Two device, no. You know who would perfectly know this? Our good friend, ChatGPT-4. Can you write some Python code for me that puts these tensors into the CUDA device? Okay, so we're going to give it this. Because I think right now, none of these are on the actual GPU. They're all just running on CPU. Okay, so we're correct. It's 2 device. And then we need to create this device object. And let's also put these here, this here. And you know what else we can do? This. For device in those two. So we're going to compare the CPU versus the GPU here. I'm going to say print device. Let's see. Okay, so we have our output here. We have first is on the CPU. We have 9x speed up after we compile, right? So after PyTorch has gone ahead and converted our little function into the faster version, right? The compiled version of our little function. You can see here 9x speed up. And then we can actually change the shape of the tensor and we get a 12x speed up. And when you're doing it on the GPU here, right, look how much faster that is, 5,000x versus 885, right? So that really shows you the difference here, right? Where getting the faster little compiled version of our function on the CPU, I mean, 10x is still faster, but it's not that much faster. But getting the little faster compiled version of our function on a GPU, we're talking 2 more orders of magnitude of speed up there. So that's way faster. Increasingly using the Triton language, we also wanted a compiler backend that used similar abstractions to PyTorch and was general purpose enough to support a wide breadth of features in PyTorch. uses a Pythonic defined by run loop level IR to map PyTorch models into generated PyTorch chord. PyTorch automatically map PyTorch models into generated Triton code. So this is what's happening here, right? This is the difference of Triton code versus CPU, right? The GPU versus CPU right here. Core loop contains only 50 operators and is implemented in PyTorch. So you can see how in the higher versions of this operator. So you can see here how PyTorch probably originally had significantly less, and then over time it bloated to around 2,000 PyTorch operators. And then here they've reduced it down to a set of 250 primitive operators. And now Torch Inductor reduces that even further to around 50 operators. So the less operators there are, the easier it is for hardware companies to design hardware that works and speeds up all your different types of deep learning compute graphs, right? If only certain parts of your compute graph can be compiled down into an operator that can run efficiently on a piece of hardware, then you're always going to be limited by the stuff that isn't able to be reduced into a smaller set of operators. Knew that we wanted to reuse the existing battle-tested PyTorch AutoGrad. The AutoGrad leverages PyTorch's torch dispatch extensibility to trace through the AutoGrad, allowing us to capture the backward pass ahead of time. Okay, the backward pass is how you actually calculate the gradient. So whenever you're feeding a batch of data into your model, you need to basically keep track of the flow that little batch of training data went through, because after that batch of training data goes through, you have to then calculate the partial derivatives of basically everything but backwards now, right? So when you're performing inference, you're going like forward through the model, and then whenever you're doing the partial differential, or no, the partial derivatives, you then have to go backwards. So here they're doing something clever there where basically they can capture the whole backward pass ahead of time. I don't exactly know what that means, but it sounds sexy. It gets the people going. This allows us to accelerate both forward and backward pass using Torch Inductor. Okay, so I guess previously you can only do one of them. Writing a backend for PyTorch. PyTorch has over 12,000 or 1,200 operators and 2,000 operators if you consider various overloads. So overloads is a concept from programming where, let's say you had a function like this, define foo, and then you had a different function that was like this, right? Both of these functions have the same name, and in Python you can't actually do this, but in other languages such as C, you could give two functions the same name and just overload them, which basically means give them different arguments, and then the compiler, right, would be able to say, okay, you passed me X and A to fooconv, that must mean you want this fooconv and not that fooconv, right? So they're saying there's 12,000 operators, but a bunch of them actually, if you pass different arguments, they do different things. So therefore, there's really over 2,000. And you can see here, I think we've actually even seen this figure before, but let me get over here. But you can see how these are all the different operators. So for example, here we're using conv2d, which is here. It's one of these convolution ones. Then we're using batch norm, which is this one here. Batch norm, there's 15 different types of batch norm, 67 different types of convolution. And then the ReLU, which is going to be activation function, somewhere out here. Tensor out, weird stuff backwards in place, base, pointwise, matmul, factory, nalg, might be under one of these. "25 message cap is lame though." What do you mean by that, Food Station? We are working on defining a smaller and stable operator sets. PyTorch programs can consistently be lowered to these operator sets. So this is interesting to note, where everyone is using transformers now, right? Everyone in computer vision is using transformers. Everyone in natural language is using transformers. Kind of transformers have taken over. But one of the benefits of that is that people who make deep learning frameworks and people who make deep learning hardware, if everyone is using transformers, it becomes a lot easier to basically make hardware that can both be used for computer vision or it can be used for natural language processing. So the seeming homogeneity of model architectures is making it easier for frameworks and hardware manufacturers to basically only support a small set of operators, which simplifies basically everyone's life. So I think there's various kind of selective pressures that are pushing deep learning to use a smaller and stable set of operators throughout all the different applications. But of course, people are going to come up with weird ops or weird specific architectures that they design for their weird specific problem. So over time, you can probably expect these to grow. Or maybe not, I don't know. E10 ops has about 750 canonical ops. We discuss more. We introduce a simple function that wraps your model and returns a compiled model, torch.compile. So why don't we rename this, and we're going to call this model. Oh, no, not model. Call it model. And what we should be able to do here is we should be able to say, actually, let's see if compiled model. Yeah, you see, GitHub Copilot is not super up to date, right? So it might not know of the existence of PyTorch 2.0. In fact, it probably doesn't know about the existence of PyTorch 2.0 at all. So you can see here that what it recommended is the just-in-time script module here, or script call, which is actually how you would do this back in the day. But now you have torch.compile. See? Let's actually see if GPT knows what this is. Can you explain this line of code? Do you know about PyTorch 2.0? Yeah, here you go. So GPT-4 does not know about PyTorch 2.0, right? Is not valid PyTorch code. There is no torch.compile function in PyTorch, which is not true, right? PyTorch 2.0 does exist. It's just that GPT does not. Yeah, the latest stable version of PyTorch is 1.9. However, new versions are released, so it is possible that PyTorch has been released since then. So there you go. Can't use GPT to help you with that. So why don't we go ahead and we actually so let's go here. And we're going to use these times. We're just cleaning up this script a little bit with a multi-cursor. But here we're going to say run model with no compilation. That's the original time. Here we're doing run model after JIT compilation, or eager, I guess. Eager. And we'll do eager speed up. Then let's do, put this here. We'll do not compile time. We'll say, yeah, we'll say that compiled, and we'll say this one eager time. This will be compiled time. After torch.compile. And here we'll say model after dynamic shape. Dynamic shape speed up. Okay. Okay, let's run this bad hombre here. Clear. No module named NumPy. Pip install NumPy. Somehow it needed NumPy. It's kind of weird. We didn't need NumPy until we used the torch.compile. Too old to be supported by the Triton, which is used as the backend. Oh no. Too old. Damn, that feels bad. Let's not do the... Damn, so you really can't even do this? Let's go like this, see if we can at least run it on the CPU here. Okay, close out of that. Okay. Model with no compilation, about 0.001. Model after eager compilation, way less than that, 15x speed up there. Model after torch compile. Why is this so much slower? I think we got some stuff wrong here. Start time, start time, start time, start time, compile time, time, compile time. That does not seem faster at all. That's slower. Yeah, somehow that got just slower. Let's comment that out, see what happens here. A little weird that that would happen. Okay, now we're seeing the right speedups that we saw before. 12x speedup, 15x speedup, 5000x speedup, 979x speedup. Built several projects. built torch.git.trace. Compiled model holds a reference to your model and compiles the forward function to a more optimized version. When compiling the model, we give a few knobs to adjust it. Mode, default, dynamic, full graph, backend. Maybe if we change the backend, it won't error out here. So here, copy paste this here. Okay, what else can we put here? Graph, model, dynamic shape tracing. Dynamic is false. Dynamic true there. Max auto tune. I wonder backend torch inductor, but a few others are available. So what other backends are available? Backend, 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 backend equals inductor. What other backends? Backend can be one of two things. Get compiler function, compiler name, lookup backend, backend. Jesus Christ. We just want a list of the backends. Come on. Lookup backend, lazy import, backends. Where's this importing it from? Let's see. And figure out a different backend to use. User 2. Is that valid? Backend, user 2. Backend string or callable. This probably is not going to work. It's still going to complain again. Key error, fuser 2. So if we do Python -pdb, I think -- debug or something like that. I forget. How could I run this Python program such that when it errors out, it gives me a Python debugger? There's like a way to Python test2.py -i. That's what I was. Okay, so Python -i test2.py. So now, boom, it errors out. Can't find it, and because we're here, right? So we can actually say backend dot keys. Where are we? Where are we? Name error, backend is not defined. What What? Let's look it up. PyTorch 2.0 backends. Torch.backends. Okay, here we go. CUDA, CNN. OpenMP. Put CUDA in there. Key error. Here's what we're going to do. We're going to edit this file. We're going to go to line 59 where it errors out here. And here's where it actually errors out. So we're going to add a line here. And we're going to say okay, so now when we run this, see it's going to break. So now we're inside the breakpoint, and now we can actually print out the backend. So let's do backends.keys. And we're going to say B for B in backends. There we go. These are all the different available backends. So we're going to copy that. Go back to our VS Code, and we're going to put that as a little comment. TVM, AOT, CUDA graphs, Dynamo Minifier, Dynamo Accuracy, Eager, TS, AOT Eager, AOT Eager, Decomp, AOT TS, Inductor, IPEX, NVP, RIMS, ONNXRT, Torch XLA. Let's try Eager, because I think that's the one that just at the beginning, and it should be fine. Assertion error. Optimize, catch errors. Innermost function, optimize context, eval frame. Assert callable. Something's going on there. It does not like that. Run that. Get rid of this line here. We don't need that anymore. Oh no, I think I know what we did wrong. This is not supposed to be here. This is supposed to be here. Yeah, that's why. We accidentally fudged up. Now let's try it. Okay, get our error there, but let's go back here and let's show that again. There you go. Okay, so this backend does work, it seems. It does seem like the Eager backend does work. Here you have your speed up. This is still really slow. I don't know. I guess maybe you need to run the model once. Let's see if that's the case. So we're going to run the model once, and then we're going to see if we get a better number for the speed up. Yeah, okay. It was the case. So you do need to run the model once after you compile it to actually get the speed up. So you see here, compiled speed up after we ran the model once versus the compiled speed up before we ran the model once. So you cannot just take your model and do torch.compile. You actually do need to run it at least once in order to get that speed up. Okay, so eager, I think, is this first one that we're doing here. And they have some disclaimers here. Full Python flexibility, user does not change code, full framework overhead, no code fusion, cannot do static analysis. Torch.compile, which is the one that we're doing here. Full Python flexibility, user doesn't change code, negligible framework overhead, code fusion on parts of the graph, static analysis, but only in parts, no pipeline parallel, and automated distributed placement. No mobile. Then torch.compile with full graph equals true. Let's try that. See if that works. Okay, so full graph, it's about there. It's about the same. Compile experiences intends to deliver the most benefits and the most flexibility in the default mode. Here's a mental model of what you get in each node. Let's look at a full example of compiling a real model and running it with code. Torch Vision. They have a ResNet 18. Torch.optim.sgd. You have your random, get on the GPU, 0 grad, compiled model, backwards step. All right, so why don't we actually copy that? And let's make a new file here. Let's make a test2, call it CNN. Let's go back to our VS Code, open up that file, test2 CNN, put that stuff in there. We don't have Torch Vision. We need a pip install Torch Vision. Go back here. We need to close out and then reopen in order for VS Code to correctly get the Torch Vision. So let's copy paste some of this code here. This code here specifically, which prints out the PyTorch version and the CUDA available. It's actually also print Torch Vision version. Torch Vision. CUDA's available, device, and let's actually do something similar to this where we try it out on the CPU and then also on the GPU. So this, then we'll say to device. So that's going to put our model on the device. Let's not do a ResNet. Let's actually do, let's see what they have. See what they have. They have AlexNets, ConvNets, Inceptions, Shuffle, Squeeze, Vision Transformer. I think that's a little bit more interesting. Vision Transformer. Why don't we do BITB16? BITL14? I want a small one. We don't want like a huge one. Let's do this one. BITB16 models dot dit b16. I guess, yeah. Let's do that. ToDevice. We have an optimizer, just your standard gradient descent. Let's actually try Atom. Like, it's the better one. The parameters of the model. So this is going to give you the parameters that are inside this vision transformer. We have a just bogus learning rate. Compile the model. This we're going to have to do the load backend eager, of course, because our GPU is too old, and then we'll do full graph true. I wonder if you can provide like the precision here. Dynamic mode. So width. Now we do want the gradient. This is ToDevice. Let's see if this one has a specific input image size that it wants. MLP dimension. Maybe it probably just reads the size of this tensor and then determines from that and builds it from that. First time you run the compiled, it compiles the model, hence it takes longer to run. Subsequent runs are fast. Okay. So for I batch in enumerate, actually we don't even need it because we're just feeding in fake data anyways. For I in range 10, let's just say that. Let's say print fake epoch to f string formatting I. And actually, let's move this down to the bottom so we can put the time. Start time. Time.time. We need to import time. And here, let's do total time equals time to time and start time. Fake epoch 1 took total time seconds. Perfect. Let's see if we can run this. Python test to CNN. All right, so we're using the right versions here. We have PyTorch 2.0 with CUDA 11.7. CUDA is available. You can see here the epochs, fake epochs. The first one takes a little bit longer, but then the subsequent ones are a little bit faster. So we can actually probably look at the watch-n 0.1 NVIDIA SMI. Catch this. So you can see here the GPU is actually working. You see, GPU fan. The memory is a little bit more full. GPU utilization at around 50%. And this is the CPU, and then this is the GPU. So why don't we actually add a print so that it's easier to see that? Let's say print device. And why don't we also do a couple new lines there just so it's easier to see. And I want to see if, let's do this, if I if I is less than 5, then we'll just have the original size. So just like this, right? But I want to see if we dynamically change the shape of this input tensor, how good the compiled model will be able to deal with it. So why don't we say random size equals torch.randomInt. No, I don't want to use torch. I want to use import random. So we'll use a different batch size here. So let's do batch size equals random randint, and then let's change that there. Okay, so now what's going to happen is that the first 5 are going to be always at 16, and then the next are going to be smaller. And let's actually also print the batch size here. And let's go ahead and run this. Let's not do 10, let's do 8, and then we'll make this less than 4, just so it prints a little bit faster. Okay, so first thing we're doing is we're using the CPU, which means that this here should not care. Go ahead and copy that, exit out, make a new terminal here, and we'll put that in there, and we'll increase the size of this so you can see. Okay, so first it's all CPU, so nothing's happening, but now you have the GPU, and you're going to see, there you go, 100% GPU utilization. And let's look here. So on the CPU, before changing the shape, roughly taking 3 seconds, then it actually was faster. And the reason it's faster is just because there's less matrix multiplies to compute, right? If you have a smaller batch size, it's going to take less time. But the important thing is that it's not, this is comparable to this, right? It's not like dynamically changing the shape of the input tensor completely screwed over the compiled model. It was able to kind of adaptively flex to handle it, is kind of what you're seeing here as well, right? First one takes 1 second, right? Because it has to actually compile the model. Then each subsequent after that is faster. I don't know why this one is, like, why is the second one much faster than these ones? I'm not sure. But then the ones after it are on par with the fast, right? This is kind of what we want to see. That's good. All right. Modes. The compiler has a few presets that tune the compiled model in different ways. Might be running a small model that is slow because of framework overhead, or you might be running a large model that barely fits into your memory. Depending on your need, you might want to use a different mode. Okay. So we have torch reduce overhead, max auto tune, or reduce overhead. Okay. Let's try those out. So let's also do this. Let's do 14 to 18 or to 16, just so it's a little bit more comparable. 14 to say 18. Random batch size. And then here, the same way that we do the CPU versus the GPU, let's put another for loop here. And we're going to say compilation mode in. And we're going to do eager. We're going to do reduce overhead. Is that how they spell it? Yep. And then we're also going to do max auto tune. And we're going to try with these different compile modes. Let's just do one new line just so it's not super crazy. And let's rerun this. Okay, so CPU with eager compile mode, this is the one that we have been looking at. So first time it runs, second time it runs, third time it runs with a dynamically changed shape. TensorBoard logger does still work because the website gives a 404 error and I can't import it. What do you mean explained? Are you trying to run TensorBoard what? Sorry, I'm trying to answer this dude here. How are you running TensorBoard? 404 means not found, so you might not be running TensorBoard. Okay, so this is no good because right here, reduce overhead. You can't find it. That's literally in the examples here. Oh, maybe it's the full graph. Maybe you can't do reduce overhead with full graph. Let's see. Let's also get rid of the eager because we know it works. Yeah, I mean, this doesn't even, it's not even in there. Backends, reduce error. Okay, so somehow I think that this one is not yet allowed. I guess let's see if auto-tune is there. It's not there. API not final. Okay, so these just aren't even there yet. That's interesting. Accessing model attributes work as they would in eager mode. You can access or modify attributes of your model, such as the weights. This is completely safe and sound. Inserts guards to check if the assumption always holds true. So you can access its attributes and modify them. Okay, so kind of what they're showcasing here is that previously, if you took your model and then compiled it, you probably wouldn't have been able to take the compiled model and then change some of the parameters. But now, the way that it's compiled, you can basically access the individual parameters and change them and still use that compiled model. Module and tensor hooks don't fully work at the moment. You can serialize the state dict of the optimized model or the model to point to the same parameters and hence are equivalent. Both these lines of code do the same thing. Let's verify it. Let's do compiled model. Let's do model. Then we'll say compiled dot model, and then here we'll say model. go back here. And here we have the compiled model. The model. Oh no, I think we might have just frozen our computer. Yeah, you see how right here at the bottom, VS Code will tell you the size of this. So compiled model is 330.28 megabytes, and then compiled model is 330.29 megabytes. So these two are both the same size. Just delete that. Explain, I'm writing a Jupyter notebook, and until last week, no module named TensorBoard. You need to install TensorBoard. PyTorch, install TensorBoard. This. I guess it comes. This is what you want. Not serialize. If you wish to save the model. Error. Okay, so you can't actually save the whole model. Damn, okay. There's like stuff that they haven't done here yet. Like this is kind of intense. Like these quarks don't actually exist. And then this doesn't quite exist yet. So there's a little bit of rough edges here on PyTorch 2.0. After generating a compiled model, run some warm-up steps before actual model serving. This helps mitigate latency spikes during initial serving. Yeah, so basically what they're saying here is that, much like kind of we discovered, you want to, after you compile your model, you want to kind of run it, because the first time it runs, it'll be slower. So they say that like if you're doing inference, right, which is basically actually doing something with the model, which is like having it actually provide outputs for certain inputs. Maybe you have some detection model in a factory, and now it's actually running in the factory versus just you're testing it. So when it's actually running, you have some script that does that. So they're advising you to actually run the model a couple times with bogus stuff in order to prevent the first people to get, or the first people to request from that model to get latency spikes because it takes longer. We will be introducing a mode called torch.exports that carefully exports the entire model in the guard for environments that need guaranteed and predictable latency. So API not final. It doesn't seem like this is going to exist. This is in the early stages in development. Compiled mode is opaque and hard to debug. You will have questions such as, why is my program crashing? Is compiled mode as accurate as eager mode? What does accurate here mean? Mean that it uses the same data types, so you can get different results? That could be kind of diverging results from eager mode. Ooh, that's kind of tricky. So I guess what they're saying here is that when you compile it, you're not necessarily, you don't know as the user what different parts of this are being converted to lower precision data types. So whenever you run this, you might be you're going to get different answers, right? diverging results, as they call it. Okay, so the mini fire. Huh. Reduces the issue you are seeing to a small snippet of code. That's kind of cool. Reproduces the original issue, and you can file a GitHub to. That's fucking badass. Where is it? Troubleshooting guide. Doesn't exist yet. That's fucking cool. Like I don't know where this is. PyTorch 2.0 mini fire. You got people running into issues already. Here you go, 4 days ago. Mini fire. Mini fire doesn't really work with symbolic shapes right now. Static shapes versus dynamic shapes. This is what we've been doing here. So this is this right here, right, where this is a static shape where you're using the same shape over and over again, and then this is the dynamic shape where the shape of the tensors is changing. So you can see here how this guy was doing the L2 norm, which is just an op, right? And he changed the size of the token, I guess, between 4 and 5, and then you can see how the eager compilation introduces numerical errors there somehow. Damn, dude, this is a server rack, right? So you normally when people make a GitHub issue like this, it's kind of standard practice to be like, here's my error, and then here's the system that I'm running it on. So you can see the system that he's running it on is PyTorch 2.0, CUDA 11.7, right? But then he's also, look at what he's running this on. He's running this on 8 NVIDIA A100, so this guy's running it on a server rack. So this is a big boy system right here. It does not change anything. It's strange. Can the reason be that I changed back to PyTorch Lightning 1.5.0? Potentially. There will be versions of PyTorch Lightning that require specific versions of TensorBoard. But import TensorBoard should. Let's see if we can actually do that here. If we do import TensorBoard. So this is what you want explained. This should always work. Looking at what was necessary to support the generality of PyTorch, one key requirement was supporting dynamic shapes, allowing models to take in tensors of different sizes without inducing recompilation every time the shape changes. As of today, we support for dynamic shapes is limited and a rapid work in progress. It is gated behind a dynamic equals true argument. We change that here. What happens if we change that? To Python S2 CNN. It's not even a CNN anymore, it's a VIT. Okay, these are all about the same. For inference with dynamic shapes, we have more coverage. Okay, so maybe it's just the dynamic shapes when you're actually training is what the issues is. See that shape changes dynamically from 4 to 256. Compiled mode is able to consistently outperform eager by 40%. Without support for dynamic shapes, a common workaround is to pad to the nearest power of 2. However, as we can see, it incurs a significant amount of performance overhead. Padding is sometimes non-trivial. So static plus padding, what this refers to is that if you have some tensor in your compute graph that is going to be changing shape, what you can do is you can say, okay, well, what's the largest size of that tensor possible? And then I'm going to just assume that it's always that largest size, and then I'm going to pad it. So if I have some input tensor that has 10 numbers, but sometimes it can be 15 or sometimes it can be 5, I'm just going to make the tensor shape 15. And then if it ever becomes 5 or 10, I just basically pad it with zeros. But here they're telling you that you no longer need to do that kind of stuff anymore because PyTorch 2.0 will deal with the fact that you have dynamic tensors, dynamic tensor shapes. Distributed. All right, here we go. Torch.distributed, 2 main distributed wrappers. You bet your ass this guy cares about distributed stuff, right? This guy who's got 8 GPUs. He definitely cares about distributed. Distributed data parallel. So this is data parallelism. And fully sharded data parallel. I don't know what the difference between these is, but work in compiled mode and provide improved performance and memory utilization relative to eager mode with some caveat and limitations. This is how many compute nodes you have. 1 node, 2 nodes. So we actually have 2 nodes on this computer, right? We have 2 GPUs. 4 nodes, 8 nodes. So 8 nodes would be something like that guy who has 8 A100s. This is the speed up. So you can see that T5, ResNet 50, these are different models. So you can see how the biggest speed ups actually happen for these language models here with the transformers. ResNet 50 and VIT, which are vision models, they have a smaller speed up. Distributed data parallel relies on overlapping all-reduce communications with backwards computation and grouping smaller per-layer all-reduce into buckets for greater efficiency. AOT autograd prevent communication overlap when combined naively, but performance is recovered by compiling separate subgraphs for each bucket. Okay, does it do that intelligently? Allowing communication ops to happen outside and in between subgraphs. EDP support in compiled mode also currently requires static graph equals false. Yeah, so there's a bunch of like extra crap that you need to put. It sounds like there's another one here called static graph. fully sharded data parallel. It's a beta feature. Has a higher level of complexity than DDP due to the ability to tune which submodules are wrapped and because they're generally more configuration options. So basically DDP is like if you're training on a couple GPUs on the same system, then I guess maybe this one is the more complicated version of that. You have a more complicated hardware mesh, right terminology. Compatibility issues with particular models or configurations are expected, but it will be highly actively improved. Particular models can be prioritized if GitHub issues are filled. Users specify an auto-wrap policy argument to indicate which submodules wrap together in an FSDP instance. Many transformers work well when each transformer block is wrapped in a separate FSDP instance. That seems really complicated, like, right? Like what? Each transformer block is wrapped? Right? Like even something like this vision transformer, there's going to be 12 transformer blocks. Depends. Dynamo will insert graph breaks and allow communication ops and forward to happen outside the graphs and in parallel. Yeah, this is the big part here. So, image am I looking at? Parallel execution in training deep learning models. It's like a specific image that I'm looking at. Not what I want. It's like I want something over time. Yeah, something like this maybe. Not what I want. Okay, I'm not going to find that image that I'm thinking of, but basically you want ops that do communication, you want them to do it in parallel to computation, right? You don't want your GPU to be waiting to receive certain information, right? That's one of the biggest bottlenecks right now in deep learning is exactly this, is basically your GPUs and your hardware are sitting there waiting for weights to come in or a batch to come in or something, some other op that requires like sending information somewhere or receiving information, these communication ops, right? So being able to do that outside of the computation, right? Outside of this graph that defines your computation and in parallel is important. Destroying this setup here. FSDP is used without wrapping submodules. It falls back on the tags. Let me reposition this. Here we go. Configuration has only been tested with Torch Dynamo. To simplify the backend integration experience, to do this, we have focused on reducing the number of operators and simplifying the semantics of the operator set necessary to bring up a PyTorch backend. Graphical form, the stack looks like this. So you have your user model script, which is this here, right? So this would be the user model script, which is coming up here at the top. And it goes through this dynamo. Then you have a graph, right? So the dynamo will compile it into a graph, which is in this torch IR, although that's not what we're using here since we're using the eager compile. Then that goes through this AOT autograd to become another computational graph, which is in a 10 or prims IR. And then that goes down even lower Here you have the actual inductor backend, right? So this is what we're feeding in here, different backends. Oh, that's probably why we couldn't do this. Wait up. We're stupid. We are no good. We had a mistake here. What we want is mode. That's what we want. Now let's see if this runs. Got an expected static graph. You guys aren't paying attention. You're letting me make mistakes. Okay, so you have your different backends. You have your different compile modes. Then that goes even lower, and it eventually becomes C++ code. Dynamically captures autograd logic and ahead of time, producing a graph of forward and backward operators in FX graph format. So this is this right here, right? You're going from your script, and it's getting compiled down into this FX graph. Right here, and then right here, and there's two different types of FX graph here. So you see here the difference between reduce overhead, which is a compilation mode where it's just trying to get rid of the overhead that's introduced by your framework, right? In this case, PyTorch. And then max auto tune is going to take longer to actually compile the model, but it should be the best possible model that you can get. So this one here theoretically should be faster than this one here, which doesn't actually look like the case, which is a little weird. It should be faster than this. Or maybe it's just a CUDA version of it. So reduce overhead, we have 1.1 and 0.049. We have 0.17, 0.50. Okay, so maybe max auto tune gets rid of the fact. So if you look here, right, the first one takes 4 seconds, the one after that takes 3.5. But when you compile in max auto tune mode, it goes 3.6, 3.6. So you get rid of that initial epoch 0, leading, same thing here, right? This is with the GPU. So with the GPU, the first epoch 1.11 and then 0.04. So you see that drastic drop with the reduce overhead, and then the max auto tune, it just starts 0.17, 0.15, or 0.5. So this behavior is weird. Like, why is the first one always way smaller? Right? Also simplify the semantics by selectively rewriting complicated PyTorch logic, including mutations, and view it as a process called functionalization. Some functional software dev was like, hey, let's just turn everything. Functional code is the future. Guaranteeing operator metadata such as shape propagation formulas. Our goal is to provide a primitive and stable set of 250 operators called PrimTorch that vendors can leverage, right? So give the hardware manufacturers a limited set of operators, and they say, hey, if you make a GPU, if you make some weird custom silicon for deep learning, as long as you can make sure to support these 250 operators, then anybody can write PyTorch code and run it on your hardware. After reducing and simplifying the operator set, backends may choose to integrate the dynamo or inductor. Vendors with existing compiler stacks may find it easier to integrate as a torch dynamo backend. Receiving an FX graph, so that it's basically saying right here, so right at this level, right, integration interface here. So this is probably, they expect vendors to build this part, and then the PyTorch Foundation should just be responsible for this. So much like the Linux Foundation isn't responsible for the actual like CPU or the GPU code or the motherboard code, right? The Linux Foundation at some point says, hey, everything below here is the responsibility of the hardware manufacturer, the hardware vendor. So similar kind of thing happening here, where the PyTorch Foundation is saying, hey, we're only responsible up until this point, and then you as the hardware vendor need to be able to accept an FX graph. Vendors can also integrate their backend directly into an inductor and further lowers them onto a loop level IR. Today, inductor provides lowering to its loop level for pointwise reduction, scatter, gather, and window operations. So these are primitive operations that are underneath a lot of the operations that you see in your favorite models. Vendors can then integrate, providing the mapping from the low-level IR to hardware-specific code. Inductor has two backends, one that generates multi-threaded CPU code, and then Triton that generates performant GPU code. These inductor backends can be used as inspiration for the alternate backends. This remains ongoing work, and we welcome feedback from early adopters. We are super excited about the direction we've taken for PyTorch 2.0 and beyond. The road to the final 2.0 release is going to be rough, but come join us on the journey early on. If you are interested in deep diving further or contributing to the compiler, please continue reading below. Okay, so it looks like they're going to have some like video chat type things going on here. Sessions, developer discussions, dev discuss PyTorch, PyTorch dev forums, performance, distributed, hardware backends, deployment. State of symbolic shapes. Oh no. This is just like the type of crap that makes like maintenance a headache. So the symbolic shapes branch. So like this guy, Easy Yang, probably made a branch of PyTorch. God, that just sounds so gross, right? So like if you go here, there's 256 branches of PyTorch. And a bunch of these are probably like starting to diverge, you know, where it's like people just actually, yeah, this is the same dude, Easy Yang. Easy Yang, Easy Yang, Easy Yang. EasyYang.com. Research engineer at Facebook AI Research. PhD at Stanford. MIT alum. This guy's badass. But he seems to have a branch where he's pushing the progress on symbolic shapes. So shapes that are defined with symbols. What else we got here? Documentation, tutorials. These are probably just the old standard tutorials. I don't think these are 2.0 tutorials. Accelerating Hugging Face and TIMM models. Makes it easy to experiment with different compiler backends to make PyTorch code faster with a single line decorator torch.compile. Can you actually do that? Yeah, so you could do it this way, right? So rather than doing it like this, right, where you compile, you pass the function here, you can basically use the pattern provided in Python, which is called a decorator, which is basically this little extra thing on top of a function that allows you to just modify this model directly rather than having to do this here and keep track of the compiled model. We expect this one-line code change to provide you with between 30% to 2x training time speedups on the vast majority of models that you're already running. So how do I make this code faster? At torch.compile. There you go. Now your model is up to 30% faster. Or it's arbitrary PyTorch code, control flow, mutation, and comes with experimental support for dynamic shapes. So excited about this development that we call it PyTorch 2.0. So control flow means that like I could have something like this. If random.randint02, no. Say if time.time.seconds or something like that. Yeah. So you could do something like this, right, where this changes randomly. So your control flow. What's changing here? There's no tricks here. We've pip installed popular libraries, ran torch compile, and that's it. Rare to get both performance and convenience, but this is why the core team finds PyTorch 2.0 so exciting. Docker. So they provide Docker images with PyTorch pre-installed. Please read Mark Sarufim's full blog story. Torch compile, getting started. Okay, so he's basically doing something similar to us. He makes like a little bogus function. Makes a little tensor, feeds the tensor into the function. Here you have the @Triton JIT compilation. Here he's doing something a little bit tricky, probably to show that the compilation still works. Please try out 2.0 and enjoy the free perf. Yeah, I mean, this is a good question. Why not just call it 1.14? I think part of it is also uh, has to do with the fact that the PyTorch is now a separate foundation, and probably some of it is like marketing as well, where there's a lot of AI news, so they want to make sure to kind of stay in the top of the news cycle. So going for a large version change rather than just a small version change like that makes it a little bit more visible. Cool, cool, cool. I'm running out of gas here. I don't know what else to do. But it seems pretty cool that we now have more and more abstracted and high level powerful frameworks. Makes it a lot easier. And also this kind of stuff was the reason that people would use JAX. So now that it's in PyTorch, perhaps we will see an even more adoption of PyTorch. Little Jax is just going around there. What is this blue one here? Mind Spore? What the fuck is Mind Spore? Fully developed by Huawei. It's like the Chinese government PyTorch. Who the fuck is using that? Kind of creepy. All right, we'll leave it on that. Hope you guys found that useful. Let me know if you guys have any questions. And feel free to drop by the Discord. We have conversations on there. Talk about deep learning, machine learning, and all the things learning. So thanks for listening. Hope you guys have a great week. Like and subscribe, and talk to you guys later.